So in the last video, we were discussing PKA and pH, and we said PKA was basically a definition that we needed to review, and the reason is because it was probably introduced to you very quickly in a 152 class, and you might walked away from that course without any understanding of PKA at all, and we need to improve that. If you are a pro on PKA, then congratulations. You are here for a review, and there's nothing wrong with that either. So we discussed this concept of strong and weak, and we said that strong acids and weak acids are at play, as well as strong bases and weak bases. I showed you a chart that had some of these acids and some of these bases ranked in order of increasing strength. And we also talked about this concept that a strong acid will make a weak base. So if you look at the left and the right hand side of the equations, then you will notice an arrow that's pointed larger in one direction or the other. And that larger pointer means something pretty special. So we did a couple of examples. We really didn't dig any deeper than that, but now it's time for us to dig a little bit deeper into this lecture theory. So one of the first things I want to say again is that in the acid-base world, it is equilibrium. So we often will see these double-headed arrows like this. It is a reversible reaction. That is why we draw one arrow with a hook that points to the right and one arrow with a hook that points to the left. And this will go back and forth, back and forth, back and forth. Over on the right-hand side, this is a irreversible reaction. That means it goes forward one direction, and that is it, folks. It cannot revert back on itself to remake the reagents that you started with. So in all of these reactions, in every one of them, you will see us draw these two-headed arrows, one pointed in opposite directions for that reason. So strong acids, strong bases, make weaker ones. Well, that also gives us an idea of which side of the equation this will prefer, because quite honestly, these arrows will point to the weaker side every single time. Okay, that is how they determine which side of the reaction it prefers. On a sheet of paper, when we write down these acids and bases like we have done in these previous examples, we compare the strengths of typically the acids, but we compare the strengths of those, and whichever one is weaker, that is the side that the reaction will prefer. The reason is because weak acids or weak bases, they do not want to revert back on themselves. That's why they're weak. They don't want to go through that process again. They're tired of it. So for instance, HCl is strong and H3O is weak. If I go to this chart and I look at HCl, it's up here at the top. If I look at H3O, it's here below. And on the acid side, these are ranked with the strongest acid on top, and then the weaker acids fall below. So H3O plus is a weaker acid than HCl. And if you look at this arrow, I'll get rid of some of that marking. If you look at the arrow, it points toward that side. And that is why that happens. That is why we do that notation, because we're letting you know it prefers the products here. And the reason it prefers the products is because the acid is the weaker acid than that one. And that means that H3O plus, it could kick off a hydrogen. It could revert back to here. But quite honestly, the HCl overpowers it and it takes over because it's stronger and it's the bully. And this H3O plus can't do anything about that. It will try. I mean, we do see an arrow here that points left. It will try to do something. It will try to gamble and see if it can get away with it. But that HCl is right back into that spot and it pushes it back to the product side as quick as it can. So this is the reason that that chart is going to be important for us. We're going to constantly refer back to this chart over and over and over. Okay, now there's another different type of chart. This one does a nice job to write down the names and the formulas, but there's another type of chart that is out there as well, and that chart is a PKA chart. So we need to talk about PKA and how does it relate to all of this strength and predicting the side of the reactions. So here's the story with PKA. In equilibria, we often say that reactions go back and forth, back and forth, back and forth, right? So these reactions will go back and forth, and KEQ is an equilibrium constant. That's what that stands for. So an equilibrium constant means that this reaction goes back and forth at a certain rate. That rate is going to stay constant. So the formations of the products, and the products will revert back to the reagents, that will convert over and over. But over time, it's going to seem like it is constant. There's going to be no change that's going to be present because this forms at a rate, this reverts back at a rate, and then they just kind of cancel each other out over time. It looks like nothing's ever changing, but in actuality it is. We're constantly getting product, and that product's constantly reverting back. So this is called the equilibrium constant for that reason. Well, in the KEQ world, there's tons of different ones. There's tons of different equilibrium. We are focused on acid and base theory. So we have an equilibrium constant that is specifically for acids, and this is called Ka. So this is going to be the acid equilibrium constant that we are referring to. And this constant has a number that is associated with it. Okay? Follow me? That number is a constant. That's why we call it acid equilibrium constant. And this number will be dependent on the chemical that we are using. So we need a table. And that table will list all of the values for those particular type of acids, if that's what we're using. Well, the problem here is that these numbers can be extremely small or maybe extremely large. But these numbers are very inconvenient to write down. I mean, who wants to write down 0.00000000000000? I mean, you get my idea, right? So we modify the number. And the way that we do that is we negative log the value. So we take the Ka value and we bring it down below and we log it and we take the negative of it. And what that gives us is a value that we call PKA. This should look familiar. And the reason is because if we have hydrogen concentration that we are trying to measure in an acid, and we log that and take the negative of it, this is called pH. So think of the P here representing negative log. So this is negative log of Ka and negative log of hydrogen. Okay, so this is one part of the problem. One part of the problem is understanding what these numbers are and what they actually mean. When we negative log these constants, if we have the raw Ka values, when we negative log them, what will happen is that we typically will get a value. And this value tends to be pretty low. You know, these are like 1s and 4s and 6s and 8s maybe. They could have pKa's of maybe 40, but they're not going to be extremely big numbers. They're also not going to be extremely small numbers either. They're not going to be super, super tiny. And the reason is because that's the purpose of negative logging them. So these are going to be much better numbers to look at, much better numbers to use in calculations, much better numbers to compare and contrast throughout the acid-base lectures. Well, I'm going to give you kind of a quick rundown, dig a little deeper in this equilibrium constant. So, in acids, we have HA, and let's say that we add water to that. We get an equilibrium that goes back and forth. This H leaves because that's the definition of the acid, and this is what we have left over. And then the H goes over to the water, and we have H3O plus. In the world of equilibrium, when you did this in Chemistry 152, KEQ always equaled the products over the reactants. That is how they always told you to set up those ice charts and to solve those equations. You take the products, you divide by the reactants. All right, well, if I take the products here, I can do that. My products are going to be A minus and H3O plus. And then my reactants are going to be H2O, and you can write these in any order, and HA. Well, the issue here is that any true liquid gets left out of the equation, okay? And water is a true liquid. You know, that is what water is. All of these other things are AQs. They're aqueous. These are things that are dissolved in water, okay? So for that reason, we have to include those. But anytime we have true solids and anytime we have true liquids, well, their concentrations are not going to change. I mean, it is what it is. So we leave those out of the equation, period. So I'm going to erase the water here. We're not going to write it because we don't include it in the calculation if we have to do one with it. So now I'm going to rewrite the KEQ. I'm still going to write A minus up at the top. That represents the concentration of that base. And then instead of H3O plus, I'm going to write down H plus. That's a shorthanded notation for H3O over the concentration of HA. And this is the equilibrium expression for the acid dissociation constant. And that's what this is over here. This is the acid dissociation constant. Now, I don't think you'll ever get a question that will ask you to do an ice chart and go through this calculation and try to do this setup. You know, that's not really what organic focuses on. I told you in the very beginning, this is very little math. It's very little equations. But I think it's important to go back and remember some of these things so you know where these values are coming from. So I could calculate a K expression, and that K constant is going to come from the concentration of A minus times the concentration of H plus divided by the concentration of HA. Basically, what this boils down to is that if we have something like HCOOH and we know the concentration of it in molarity, that will give off some of its proton, right? And that proton can be measured. And we can measure that very easily. And that could be just simply a pH probe. So we can measure the pH of that solution. We could get the hydrogen concentration that it spit out. And then we could look at the base that is left over. Because if it did spit out a proton, we have formed a conjugate base. And that is what the A minus represents. So it's just really an equation that involves some numbers. Those are concentrations, and it's concentrations of the acid together, and then it's the concentration of the hydrogen that it spit off, and then the corresponding base that is left over when it does spit off a proton. That is what that equation represents, all right? So, because again, we're dealing with acid-base chemistry, this is properly referred to as Ka. We can negative log this value, and then we can get pKa, and that's where that value comes from. So on the screen right now, you are seeing PKA values of various types of categories of acids. Very strong acids have PKAs less than 1. Moderately strong, PKAs of 1 to 3. Weak, PKAs of 3 to 5. Very weak, PKA 5 to 15. And extremely weak, PKAs greater than 15. So PKA, if we have the PKA values, we look at them. What are they? Because this gives rise to an idea of strength. If you correspond this to the pH scale, 7's neutral. Anything lower than 7 we said was acidic, right? So if you look at the pKa's, it kind of matches that. Up to 3 to 5, these are weak acids. So at pH of 5 or lower, we would still classify those as acidic, wouldn't we? And if I gave you a question and I said you had a pH of 4 and you had a pH of 2, which one is more acidic? You would tell me, pH of 2 is more acidic, right? It's closer to the left from that 1 to 4 scale. pH of 2 is pretty acidic compared to the 4. Do not let pKa confuse you because it's the same stuff, folks. There's no difference. So if I said you had a pKa of a 4 and a pKa of a 2, which one is more acidic? You would use the same reasoning and you would say pKa of 2 is more acidic. It is stronger. And stronger means it spits off a proton. And if it spits off a proton, by definition, it is an acid. So this is one of the ways that we use PKA values. It is a table that we can look up. These are values. Sometimes we use so many acids all the time that we have these pKa's memorized. I'm not asking you to do that, but this value is related to strength of the acid. Now here's the thing. If the acid is classified as strong, pure blown strong, those were really the 7 that we talked about here. These normally do not have pKa values, okay? They give off all the proton. They're not going to hold any behind. And pKa is really a measure of how much proton that it does give off. So because these give off all of it and they don't hold any behind, then we just don't really worry about pKa's with these, okay? But if they are weak, which is the majority of the acids that we have in the lab, if they are weak acids, they do not give off all the proton. If they don't give off all the proton, then we have to have a way to measure how much proton they do give off. And that's the purpose of pKa. How much proton does it really give off in solution if we decide to use it? But it's only for weaks, not for strongs. And you have to keep that in mind. So don't let that confuse you, all right? So if I try to go and look up the pKa for hydrochloric acid, I probably could find a value for it. But, quite honestly, it's pretty silly because we never need to use that value for anything else at all. But if I'm using a weak acid in a lab, there is a chance that I would need to calculate how much hydrogen that stuff would give off according to my reaction. So that is the way that we can use pKa. It's also going to be used to help predict the reactions that we were given and that we've done examples for. So remember that whole concept of having reagents over here and products over here and going back and forth, back and forth, back and forth. I told you that you could use this chart as a way to figure out which side of the reaction is going to be preferred. Well, you can also use pKa's because that's how that chart is built. So if you have pKa's in front of you, you can also use those values to determine which side of the reaction it prefers. Remember, it always goes to the weaker acid, and that's the one that we look at most of the time, or base. So if I have an acid over here, and this acid has a pKa of, let's say, 40, and on this side, I have identified the acid. Of course, it would be maybe a conjugate acid, but it's still an acid. And if this pKa was 3, I would look at these two numbers and say, whoa, this pKa of 3, that's just like pH here. This one is more acidic. This one is stronger. So therefore, this reaction would go left-handed, because this one is the most acidic, and because that one's the most acidic, that one is the strongest, and because this one is the strongest, then poof, it pushes over here to the weaker side. And this is a weaker acid because this pKa is listed at 40. I just made that number up, but if you don't like to see that 40 because it's too big, then we can change that. Let's just write a 7 here. Maybe that will make you feel a little bit better. It means the same thing. There's no difference. So the reaction always goes to the side of the weaker ones. And pKa is a way that we can measure and quantify this stuff. Really confirm that, yes, this is the side of the reaction that we need. In addition to that, the pKa tables, they're pretty large. There's a lot of information in them. There's tons and tons of different listings. All of the acids are going to be there. This chart is a very abbreviated chart. So there is a chance that this chart does not include the acids that we need to use or that we need to compare with each other. And if it's not on this sheet, no big deal. There is a master sheet that you would typically find in the back of a general chemistry text. I don't think it's in the back of the organic text because, quite honestly, I don't think we even use it and go that far. What you'll be using will be here on the chart for the most part. But there is a table of PKA values, and that's why we have them, because this abbreviated chart doesn't quite help us every single time. So in the next video, we'll pick up with this example, and we'll take a look at these equations, and we'll talk about acids, bases, conjugates, and why the arrows are drawn the way that they are to make sure that we can really predict which side is stronger and which side is weaker. So come back to me, and that's what we'll talk about next.